Hi class, and welcome back. Today's album recommendation is the album Almost by the Ophelias, which is just an excellent all-female band. Great songs, really catchy. Yeah, I think this came out in 2018, and I remember it being just an earworm for me of songs I could not get out of my head. So today we are talking about the divergence theorem, and the divergence theorem, fortunately, we already know what divergence is, so this theorem is going to be somewhat easy to understand in the context of all the other things we've done so far in the class. And so let's review that a little bit. So we started off by defining our first sorts of line integrals looked something like this. And we had examples, this was like the flow along a curve. And so C is a curve in both these examples. And then we also ended up looking at the flux across a curve, and we made sense of this. And so dp points in the tangent direction to the curve because p is parameterizing it, and dn is pointing in the orthogonal direction to the curve. And that's how it makes sense that these are measuring flow along and flux across. And also we've introduced surface integrals. In particular, we introduced this idea of a flux across the surface integral. So if f is going across some surface and n hat is an unit vector pointing in the pointing normally off of the surface, so orthogonal to the surface, following our positive orientation convention, then f dot n hat is going to measure how much of f is going normal to the surface. And so when you add those all up, you get the flux across the surface. And this is an example of a surface integral. And if the surface is parameterized by p, and it's a two-dimensional surface, so you've got u and v as your coordinates, then you have this nice form of it. And you should think about this as giving you a normal vector. Parameterized, so it gives you a normal vector at the point parameterized by u comma v on the surface. So normal vector for p of u v. Now, the reason we focused in on these types of examples is because for each of these specific types of line integrals, so either a flow line integral or a flux line integral for a vector field, or the flux across a surface, we came up with sort of corresponding examples of fundamental theorems of calculus. And let's recall all of those as well. And so our fundamental theorems of calculus look something like, we have the fundamental theorem of calculus, the ordinary one. So if you have a derivative of a function and you integrate it, you get just f of b minus f of a. So you take the antiderivative. And then we also had one for line integrals. That said, okay, the thing that corresponds to integrals of derivatives, so derivatives are easy in this fundamental theorem of calculus, so you can take an integral of a derivative very easily because you know the antiderivative. If you have a gradient vector field, you can compute the results on the other side. So here we have gradient vector field, which is producing a form of the fundamental theorem of calculus for line integrals. And you also compute it just by evaluating at the two endpoints. And I said that, in some sense, these are reducing dimension. So both of these right-hand sides you should think of as being zero-dimensional integrals. So they're just sums of values at points. And points have no dimension to them, which is why they're zero-dimensional. Now, a little bit more complicated, we had these two versions of Green's theorem. So this was Green's theorem. And we had, in this first case, we had the flow form, which correspond to being curl. And you can think about this as curl is measuring kind of like local circulation. And so if in fact, the curve is really small, the flow along the curve is going to look identical to the curl around the region. And so that's how you make sense of these two sides. And so over here on this left-hand side, we have this, here's curl. But we also had this divergence form for it, the same integral. So this was the flux or divergence form of Green's theorem. And you can also imagine if your region is really small, then the divergence is measuring how much flow there is going out, which is going to be the same as how much is crossing this curve C. So that's why divergence pairs with flux. So the divergence theorem that we're going to introduce today will be yet another fundamental theorem of calculus. So let's make note of that. So what does that look like? Well, the divergence theorem, it's going to involve divergence. And the question is just what type of divergence. So we have taken divergences and we define divergence for when f is a 2- or 3-dimensional vector field. And so this is now going to be one where the divergence is 3-dimensional. And so the left-hand side is going to integrate over some big region, a triple integral of whatever the divergence is at that point, dv. And so when you take a dot product, the divergence is now a scalar-valued function. So it makes sense to add it up as an integral. And on the right-hand side, we have, well, because this is a fundamental theorem of calculus, if we're going over here from divergence and a 3-dimensional integral, we expect over here to get a 2-dimensional integral. And it should be something simpler. So we should, if we have divergence of f, over here, this should be more or less just the flux of f, because divergence is measuring flow across small regions. So what's the flux form of the integral? It's going to be f dot n hat ds over some boundary of R. So the one thing that's subtle here, and I'm going to draw a picture, is what does R have to look like? And we want to think back to Green's theorem. So for Green's theorem, our curve needs to be a closed curve. So what we need here is that R is a 3-dimensional region with boundary, which is closed, boundary R. And we'll talk about orientations in a moment, but what that means R looks like is maybe, here's a kind of 3-dimensional region. It's like a donut with a blob coming off of it. So this might be what R looks like. And maybe if I wireframed it, I might have I could draw some level set for this region, something like that. And R is solid, so I'm actually looking at, because it's a 3-dimensional region, I'm actually looking at this solid deformed donut. Shading, shading, shading. So solid regions can have boundaries, and their boundaries are going to be two-dimensional surfaces. So if this is R, then the boundary of R is, let me attempt to draw this again, is the actual boundary of it. So it's all of this stuff on the surface. And we're going to assume that it's outward normal. Oriented. So because R is a three-dimensional region, and it's going to have to be a bounded region, then in order for its boundary to exist and be closed, closed means that it has no boundary of its own. You get these sorts of, this guarantee that you can pick an outward normal. So you should imagine over here that your generic point in R somewhere, it's got three directions it can move in. But at some point it runs into a point on the surface, and then there's essentially only like two directions it can move in tangent to the surface, and one direction that is normal to the surface, and coming off both of those as right angles. So let's draw this for a sphere, which is a region people should make sense of. So here's just more example pictures. So if you pick the solid ball, ta-da, I shaded it to indicate it's solid. So this is a solid ball. So an equation for that might be like x, y, z, such that, oh, my pen stylus is dying, such that x squared plus y squared plus z squared is less than or equal to 1 would work. And so this less than or equal means I have to fill the interior of the ball. Then the boundary of, so let's call this B. The boundary of B is the sphere. So that's x, y, such that x squared plus y squared, oh, comma z, plus z squared equals 1. And if it equals 1, it's only the boundary of the sphere, not the interior. So you should imagine that the points in B either have interior points, which have kind of three directions, three independent directions that they can move around in and still be within B. And then it has boundary points, which have kind of like two directions that they can move around in still within B. And then another direction, which is outward, which makes them leave B. And so by picking the outward normal orientation, we kind of always fix this outward orientation. So in with these kind of as running examples, so like for the sphere, the divergence theorem, the divergence theorem tells us that if we have a vector field F, in R3, it's any three-dimensional vector field, then if we want to compute the flux, vector field in R3, that's continuous, with continuous derivatives, which we always need in order to do any of these theorems. So given a vector field in R3 with continuous derivatives, you can compute the flux across the sphere with the outward normal orientation. So that would be f dot n hat ds as the triple integral over the ball B the solid ball, of the divergence. So the divergence of f dv. And you just add up all these divergences at each little place in the ball, and you'll get some number. The only thing I want to still mention is, just like in Green's theorem, if we have a surface integral where the surface itself has no boundary, we're going to use a little loop to denote that it's closed. And so, just kind of as an aside, this means no boundary on the surface. So the sphere works fine, but you can't take a surface which is a rectangle because it itself has a boundary. So you need to pick something where it has no boundary points of its own. So you can't pick something that you can then use in Green's theorem, basically. To give some context for the divergence theorem, it actually kind of goes back to Gauss's law. So Gauss wrote this as saying the total of the electric flux out of a closed surface is equal to the charge enclosed divided by the permittivity. So you should read this as the electric flux out of a closed surface, that's some surface flux integral. And then that's equal to the charge enclosed divided by the permittivity. The permittivity is some sort of property of the solid, and the charge enclosed is some sort of integral over the region bounded by the surface. So that's some triple integral of charge density, like per unit volume. So if you came up with some function for that, dv over this region, you would get this charge enclosed by adding up all your little microscopic charges. So this is divergence, knowing that the flux out of the surface has something to do with this charge density is telling you that the flux out has to do with the rate at which the density is changing. So as electrons are crossing the boundary, what is the that determines your electric flux. So for some fun math history, Lagrange discovered this rule in 1762, and then Gauss in 1813, quite a bit later, rediscovered it totally independently. He hadn't read Lagrange. By the way, that is the Lagrange of Lagrange multipliers. Then a third mathematician, Ostrogradsky, in 1826, rediscovered the theorem again completely independently, but he was the first person to actually write down a proof for this, a formal mathematical argument for why it's true. And then Green, when he was kind of flying through and proving his theorem, his Green's theorem for line integrals, he discovered this also as well in the context of electromagnetism in 1828. Didn't offer a proof, but I think he did offer proof, but it had already been proven once. But he hadn't read any of the previous references. So you can see that there's this huge 80-year history of people not reading each other's work and just reproducing known results. So, you could get your name on anything back then. So let's just leave that as context. Let's look at some examples. So let's first start with an example that we considered last time. So we took the sphere, x squared plus y squared plus z squared equals 9, so sphere of radius 3, and the radiation field 0, 0, 2z over 9. And we computed the flux across the sphere by parametrizing the sphere and doing some work. But we now know that the sphere is a closed surface, and it bounds a ball. So let's treat the problem that way. So let B be the ball x, y, z, x squared plus y squared plus z squared less than or equal to 9. So the ball of radius 3. So boundary of the ball is the sphere that we considered. So this guy is boundary ball. I'm going to let the field be f. And then what we want is the integral. Well, it's over a closed surface, so I'll do the little loop. Nope, I said boundary B for the sphere of f dot n hat ds. But I don't want to even parameterize the sphere, so I'm just going to use the divergence theorem to pass to the triple integral over B of the divergence of f dv. And so what's the divergence of f? So remember, that's nabla dot f, which means I'm taking each partial derivative of f. So if I write nabla as d dx, d dy, d dz, and f is 0, 0, 2/9 z, then each of these partial derivatives gives me 0 for the x1 plus 0 for the y1 plus 2/9 for the z1, which is, oh, so nice. That's just 2/9. So this whole integral that we wanted is just the triple integral of 2/9 dv over b. So if I remember my formula for the volume of a ball, which I do, it's 4/3 pi r cubed, then this is just 2/9 of that. So my answer is 2/9 times 4/3 pi, and r here is 3 cubed. So what does that become? 8, 3 cubed, I got 3, I've got 9, which is 2 3s, and another 3, those all cancel, so I get 8 pi. And you can flip back to Monday's lecture and discover that, in fact, this is what we computed before with parameterizations. But you'll notice here that this was way, way, way easier, because the fundamental theorem of calculus always lets us take something that's hard and make it easier if we're using it the right way. Example 2. Let f be the vector field 4y squared, comma 3x minus cosine x, comma z squared minus x, and let R be this region. If you notice, all these inequalities have constant bounds, so R is a cube of side length 2 in each direction. So it starts from x equals -1 to x equals +1, y equals -1 to y equals +1, etc. So it's a cube of radius 2, of side length 2, centered at the origin. I want the flux across the surface of R, and what surface of R means, this is kind of imprecise, but this is how English works, is I want the boundary of R. Well, R's a cube, so if I were, so here's what R looks like. So if I were to compute the flux across the surface, what I would need to do is split up the integral of the flux into many different integrals, one for each side. So you'd have to subdivide this into like the front face and leave out the other ones, right? Of f dot n hat ds, and you'd have to come up with a parameterization for that front face, plus the back one, plus the left, plus the right, plus the top, and plus the bottom, because, and those have the same sort of integrands for all of them, because R has these edges, and so every time you run into a corner like that, you're going to have to switch parameterizations. Well, this seems nasty, and I don't particularly like parameterizing anything, even though planes are not that bad. So let me use divergence theorem to figure out that, in fact, the flux will equal the triple integral over R of the divergence of f dv. And I compute the divergence of f. Well, each of f's components actually, the first one, the x component only has y, so dx is 0. The second one only has x's, so dy is 0. And the third one does have a z, so ddz is 2z. So this is just the triple integral of 2z d z dx dy. And I guess I wrote it in a funny way. Let me go dz dy dx. X goes from -1 to 1, y goes from -1 to 1, and z goes from -1 to 1. Those are rectangular bounds, so I can take each of these integrals separately. So my answer is going to be, for the z component, I get z squared, definitely, as my integral. So that's z squared, evaluated from -1 to 1. For y, I get, for dy, I get a y evaluated from -1 to 1. And for dx, I get an x evaluated from -1 to 1. So z squared at 1 and -1 is the same. It's both equal to 0. And then, sorry, they both equal 1. So this is 1 squared minus 1. For the y component, I get 1 minus -1. And for the x component, I get 1 minus -1. So that's 0 in total. So, and the 0 is really just coming from this first one component. Yeah, so you can also see that if you divided this region into, if you made the z-axis go up, if this here is z equals 0, then 2z is both positive up here and negative down here. And so, like, 2z symmetrically on the top gives you some positive amount, and on the bottom gives you an equal and opposite negative amount, so they cancel. And that's what's happening in this cancellation. For problem 3, I'm going to take the vector field to be x cubed, y cubed, z cubed, so for each component, and then R to be this following region. So maybe pause here, try to draw it, try to re-express the integral. So for me, R, I see that it's the first part of this, x squared plus y squared plus z squared is less than or equal to 1, that would give me a disk. And the second part is telling me z has to be positive. So it is the positive half of the solid 3-ball. So let's draw that. So R looks like this region. So it's the top half of the solid 3-ball. And the ball has radius 1. So if I were to draw axes, here's the origin. Here's the x-axis. Here's the y-axis, and here's the positive z-axis. And all of those are 1. So the surface of R has actually 2 components. So the boundary of R looks like, on one hand, you've got this top half of the ball, where it's, let me just try to sketch some lines on this to make it clear what I want. So I'm giving it a skeleton. So it's just kind of this, this half of the sphere. So it's the top half of the sphere, but it also has this bottom, which is a flat disk. And if you're orienting the boundary of R, you always use the outwards normal. So the top is oriented like that, your kind of standard outward orientation on the sphere. But I'm only taking half the sphere. But this disk is oriented down. So this is like the unit disk in the xy plane, but oriented down. And so you might say that orientation is negative of the standard orientation. But this is the top half of the unit sphere with the standard positive outward orientation. So I'm trying to be really explicit about these orientations, even in these problems where they maybe don't matter, because they're going to come back for Stokes' theorem on Friday. So it's really important to be thinking about these orientations. So that's what the outward normal looks like. So if I want to compute the flux across this boundary, you'd have to parameterize each half of these boundaries separately and then add them up. You could totally do this. I mean, we've done the sphere before using spherical coordinates, and you could do the disk as well using just x and y. But it's always worth checking whether divergence theorem makes your life easier. So the divergence theorem tells me that the flux, which is this double integral over the boundary of R of f dot n hat ds, is equal to the triple integral over the whole solid region R of the divergence of f dv. And since the divergence of f is pretty easy to compute here, it's just 3x squared plus 3y squared plus 3z squared. I'm looking at that, I'm like, that's probably the better integral to compute than having to do these two different integrals where I have to parameterize one surface and a different surface. In fact, I look at this and I say, hey, I'm in a solid ball. That's a region that I can describe using spherical coordinates, and x squared plus y squared plus z squared is rho squared. So turning this into spherical coordinates is the way to go. Here's a big dv. So let's do that. So in spherical coordinates, this integral looks like, I'm going to pull the 3 out in front, and then it's the triple integral over the region, and we'll describe it in a second, of just rho squared, and dv is rho squared sine phi d rho d phi d theta. So, that doesn't look that bad. And my region becomes, in spherical coordinates, theta is going between 0 and 2 pi, because I have full symmetry around the z-axis. Phi starts at 0, that's the z-axis, but it stops at pi over 2, which is the xy plane. It doesn't go all the way to the negative z-axis, which would be pi. And rho is starting at 0 and going out to 1, because it's my radius. And then I'm left with, so those are constant bounds, which is the best type of integral we can have. I've got rho to the 4th, d rho. Then I've got this sine phi d phi integral. And finally, I've got a d theta integral. And because these are constant bounds, I can do them in any order I want. So let's just do them all at once. So I get 3. For theta, I get 2 pi minus 0, because I get theta evaluated from 0 to 2 pi. For sine of phi, I get minus cosine, evaluated from 0 to pi over 2. So minus cosine of pi over 2 minus cosine of 0. And for my last coordinate, I have rho to the 4th. That becomes a rho 1/5 rho to the 5th, evaluated from 0 to 1. So that's 1 to the 5th minus 1/5, 0 to the 5th. So here's minus cosine of phi, evaluated from 0 to pi over 2. And here's 1/5 rho to the 5th, evaluated from 0 to 1. So my final answer is 3 times 2 pi. Cosine of pi over 2 is 0, and cosine of 0 is 1. So I'm at times 1 times, and then this is 1/5. So that was really not that bad. I end up with 6/5 pi. So if we zoom out, you can see that, like, this was really a pretty easy integral to compute. I just had to convert to spherical coordinates. And if I had to do either of these parameterizations, I would still be working out how to compute the cross product to get the normal vector, probably for the sphere at this point. And we'd have to use spherical coordinates for that anyway, so, like, this is clearly less work. Okay, so I've now made F a little harder and R a little harder. Maybe take a pause right here and try to draw R, and then also the computer integral. So I look at this, and what I want to do is, z is not squared, so I would think of this as being z is less than or equal to 4 minus x squared minus y squared. And 4 minus x squared minus y squared I recognize as being a paraboloid. And it's a downward one. So my picture for R is that I've got a downward facing paraboloid, and it keeps going forever. But I'm only taking z between 0 and 1. And so, because the z is less than or equal to, I'm underneath. So the region is underneath of this graph. So underneath, right? Not above, because z has to be less than this graph. Z, though, is only allowed to be between 0 and 1. So if you set z equal to 0 and z equal to 1 in this equation, what you get is x squared plus y squared is less than or equal to 4 minus 0, which is 4. So that's a disk of radius 2. And at z equals 1, at a height 1, we get x squared plus y squared less than or equal to 4 minus 1, which is 3. So disk of radius square root of 3. So what that means is at, my two heights, I've got like, draw them in red and yellow. So on one hand, I've got this height. At height z equals 0, I'm at a disk of radius 2, and at height z equals 1, I'm at this square root 3 disk. And so the region I actually care about, R, is in between these two. So it looks something like this. So it's like I've taken this paraboloid and I cut it at two heights, and so I've ended up with like a little sausage, thing. So just to be clear, I've got this kind of top disk at height z equals 1, and then my sides look like kind of like a piece of a rocket ship or something, and that's what R looks like. So I always forget what these are called. I think it's like a truncated paraboloid or frustrum. I don't know. Doesn't matter. It's this region R. So this looks truly bad to try to parameterize, so I'm just going to skip to using the divergence theorem. So it should probably be the triple integral over R of the flux, or sorry, the divergence of f dv. And the divergence of f is it's 0 plus x squared from the d dy component plus, and then d dz gives me y squared dv. So because of that x squared plus y squared, I'm going to convert this to cylindrical coordinates. Because also I see that I have rotational symmetry in the xy plane. So let's now just treat this integral like one we're doing independently. So I've got this triple integral over R of x squared plus y squared dv. I'm going to pass to cylindrical coordinates. So let me give myself room. That's r squared. dv becomes r dr d theta dz, and I think it's standard to put the dz first, so let me do that. R dz dr d theta. So I'm really just putting the x and y's in polar coordinates. So the way I look at this, I'm going to use this bottom guy as my base. And so and that one had radius 2. So my ranges for theta are between 0 and 2 pi. R goes between 0 and 2. And then I have to decide, okay, what are my z bounds? And in the zr plane, the base was at z equals 0. So I should definitely start there. Let me draw in blue. So here's my base. Ooh, base going out to 2. And then up here, I'm only going out to square root of 3. And in between them, I am tracing out this parabola. Sorry, I'm trying to dot it to show that it's like a parabola coming in. Right. And to be clear, that is, if I rewrite my original constraint equation as r squared plus z less than or equal to 4, this therefore has to be z equals 4 minus r squared. But because of this, you realize that you have to change integrals at this point because your upper bounds are changing for z. So I can't do this as one integral, I have to do it as two separate integrals. which is totally fine. So what do those look like? Just give myself a little bit more room. So my integral, so theta goes from 0 to 2 pi. R goes from 0 to 2. For the first one, let's just label it 1 here. R starts at 0 and goes, Z starts at 0 and goes up to 1. And I'm integrating r cubed dz dr d theta. And for the other one, I'm going from theta equals 0 to 2 pi, r from 0 to 2. Oh, sorry. I'm going to rectify this. My r bounds change. So r is going up to root 3 in this first problem, in this first integral. So r is going up to root 3. And then r starts at root 3 and goes up to 2 in the second integral. And when you're at a given r height, your z coordinates start at 0 and go up to 4 minus r squared. And so our integral here is r cubed dz dr d theta. And each of these we can compute separately. I'm kind of out of space, so maybe I'll just go to another page. Okay, here are my integrals. Let's just treat this left one first. So I get, all the bounds here are constant, so I'm just going to integrate each of them separately. So for theta, I get 2 pi minus 0 is just 2 pi. For r dr, I get r cubed dr, I get r to the 4th times a quarter. So 1/4, r to the 4th evaluated from 0 to root 3. I'm just going to get the radical 3 to the 4th minus 0. And then for z, I get 1 minus 0, so that's just times 1. For the second integral, things are a little more complicated because I have this r up here in the dz coordinates. So if I evaluate dz first, I get z, and then I get 4 minus r squared when I evaluate it. So I'm going to get integral 0 to 2 pi for theta, integral r equals root 3 to 2, and then from z, I got a 4 minus r squared, r cubed, dr d theta. And now I'm down to constant bounds. So my final answer is going to be, let's see, over here I got pi over 2 times 3 to the 1/2 times 4, so that's 4 halves, which is just 3 squared. It's somewhat simpler. Plus, and then for theta, I'm getting 2 pi. And for r, I'm getting 4r cubed minus r to the 5th. Before integrating. So that's going to be 4/4 r to the 4th and 1/6 r to the 6th, evaluated from radical 3 to 2. So my final answer is, 9 halves pi plus 2 pi times 2 to the 4th minus 2 to the 6th over 6 minus quantity 3 to the 1/2 to the 4th, so that's 9 minus 1/6 3 cubed. And we're just done. Like, I'm fine with that. Okay, and that's probably as hard as we're going to get today. So let's just stop there. And on Friday, we're going to talk about Stokes' theorem, which will be yet another fundamental theorem of calculus. And then next week, we're going to kind of sketch a suggestion that we don't have just... This is not the end of the list of fundamental theorems of calculus. we're going to come up with a way to reason out how to get infinitely many new versions of the fundamental theorem of calculus, and that will be so exciting. But first, the computational result that's really useful, which is Stokes' theorem, coming up on Friday.